Hello, my name is Katarina, and I'm happy to present our work on multi-contact task and motion planning, guided by video demonstration. Task and motion planning remains a challenging problem, especially for tasks where an object needs to pass through a narrow passage. The motivation of this work is to speed up pathfinding by providing a demonstration of the task, shown here on the left, to obtain a robot trajectory for solving the task, shown here on the right. In recent years, there has been a significant amount of research in the task and motion planning field. However, one of the limitations of the previous works is that they are mostly focused on 2D tabletop manipulation. A current method that goes beyond 2D rearrangement planning is PDDL stream. However, it still has the limitations of sampling-based methods, such as difficulty in finding narrow passages in the configuration space. Humanoid Path Planner, or HPP, searches a path in an admissible configuration space, a set of manifolds defined by placement and grasp numerical constraints. Our work builds on top of HPP by constructing these manifolds from an input video demonstration. Policy search methods, for example reinforcement learning, are widely used to solve manipulation tasks. However, these methods usually require substantial training time and require relearning if the scene is changed, for example if the furniture is moved. In our work, we rely on a geometry-based planning approach for solving manipulation tasks. We use video to guide the planning algorithm in tasks with multi-contact rearrangement and narrow passages. Input to the proposed approach is a video of a human manipulating objects. From the video, we estimate object 6D poses and human object context states. We use the estimated values to construct configuration space for the planner. The configuration space is composed of placement states in which all objects lie on the contact surfaces and grasp states in which one object is grasped and manipulated by the robot. The first placement state P1 is initialized from the starting object poses. After one object is moved, a new placement state P2 is initialized. There are several ways to grasp the object, which initialize different grasp states. For example, here we define two grasps from the top G1 and from the side G2. Goal object poses initialize final placement state P3, together with the grasp states G3 and G4. We design an extension of the RT algorithm that samples multiple trees with roots at the intersections of the states. The algorithm effectively searches for the path between the start and goal configurations in the constructed admissible configuration space. Once the path is found, we execute it in simulation or on the real robot. Here you can see execution on the real robot. The yellow progress bar shows to each state the current configuration belongs. The robot starts from the initial configuration, proceeds to grasp the first object, releases the first object on the goal pose, moves to grasp the second object, and after releasing it at the goal pose, moves to the goal configuration. To test our approach, we designed a new benchmark consisting of 3 challenging tasks that involve multiple pick-and-place actions. In the shelf task, objects need to be moved to a predefined pose on the table or on the shelf. In the tunnel task, a single object should be transferred through the narrow tunnel. Tasks with narrow passages are a major challenge for sampling-based planners. The waiter task simulates the job of a waiter, in which a set of objects need to be transferred from one location to another. Waiters use a tray to minimize the walk distance. To compare the proposed approach with the baselines, we use the following metrics: the success rate in solving the task, the time to find a solution, the length of the planned path, and the number of object grasps and releases, so the number of contacts. Next, we present the remaining result of the Panda robot experiment. The input video with the estimated object poses and contact states is depicted on the left, and the planned robot trajectory executed on the real robot is on the right. The robot base pose is fixed to be on the table. We also solve challenging tasks with a narrow passage. Next, you can see examples of the VR5 robot in the simulation. The robot base pose is sampled such that all objects are reachable both in the start and the goal poses. The task with multiple objects is very challenging for planners, as one needs to discover the sequence of object rearrangements. We overcome the challenge by extracting information from the video demonstration. Finally, you can see examples of the KUKA robot on the moving platform. The platform moves on the plane. In the shelf task with 2 objects, the robot can only reach objects from opposite sides of the table, and therefore planner needs to utilize the platform motion. In the waiter task, the robot puts all objects on the tray to transfer them onto a shelf simultaneously. We compare the proposed approach with the following baselines: RT Connect implemented in HPP without and with path optimization, PDDL stream method, and the proposed approach without and with path optimization. HPP fails to solve shelf task for more than one object in the given time limit. Our method outperforms the PDDL stream planner based on the success rate. And for the tunnel task, the state-of-the-art planners fail to solve the task due to the difficulty of discovering the narrow passage. The proposed approach takes advantage of the available demonstration to discover the narrow passage and manages to find a path for the non-mobile robots. Refer to the paper for more detailed discussion of the results. Thank you very much for your attention.